Hello and welcome. In this video we will keep this perspective of the element plate theory, but this time we aim a different thing. This time we are looking at the forces at the plate elements in order to transmit the maximum possible power from the wind to the movement of the rotor blades. And therefore again we use the same picture of the complete wind turbine and converting that view only to a single plate element.
In this picture you can see again a wind energy plant, and the wind is again coming from ahead in Z direction and the rotor blades are rotating counterclockwise in the XY plane. You can see a cross section in the left rotor blade, and here in the right picture you can see the same cross section but a bit bigger and slightly rotated around the Y axis. And the wind is blowing from the left side in Z direction again, what makes the rotor move downwards in rotating direction. In this picture you can again see the cross section of the blade profile, and with the help of this picture I will now explain the relevant forces that affect the blade element. The red vector shows the drag force in direction of the resulting velocity Vr. The force is calculated by the following formula. Thus it depends on the density of the air, the rotor blade depth Tb, the resulting velocity Vr to the power of 2, the drag force coefficient Cw, and the depth of one blade element dr. The drag force coefficient is a dimensionless measure for the drag of a body. It depends on the angle of attack alpha and is usually determined experimentally in a wind channel. The perpendicular lift force is shown in green. It is calculated by the following formula. Thus it also depends on the air density, the rotor blade depth Tb, the resulting velocity Vr to the power of 2, and the depth of the blade element dr. Additionally, it depends on the lift force coefficient Ca. This coefficient is a dimensionless measure for the lift of a body, and it also depends on the angle of attack alpha and is usually determined experimentally in the wind channel. The force resulting from the lift and the drag force is shown in blue, and this force is calculated by a vector addition of the lift and the drag force. The resulting force can be divided in an axial and a tangential component.
But the forces that we just have seen and demonstrated by Hannah is not pointing in the right directions we are interested in. Therefore, we can derive those forces in a different direction. And what we are interested most is this tangential force, this yellow vector that points in the direction of the rotation of the wind turbine. And that is the one we are really looking for. And therefore we can pronounce this dft equal to 1/2 rho times Tb times Vr to the square times Ca sine of delta minus Cw cosine of delta, and times the thickness of this rotor blade element dr. And additionally we can look to the force, the thrust, that goes in direction of the wind speed, that is willing to move the turbine down, and that is then dFax is equal to 1/2 rho times Tb times Vr to the square, and then in brackets Ca times cosine of delta plus Cw sine of delta times again dr. To have a look on a picture of a wind turbine, and again this picture shows us this turbine that is not in movement, it's in a standstill. We still can see this in the position of the rotor blades, and when the wind is approaching here the turbine, we have the air drag here, we can see in this vector, and perpendicular to that we have then the lift force, and the sum of it is the total air force. and that then would start the turbine to move. When we change now the perspective to this turbine that is in movement, that is rotating clockwise, there we again have a shortcut of the rotor blade, and then we again can have a look to the forces. We have this red one, the air drag is going into a direction of the resulting wind velocity, and perpendicular to that we have then the lift force of the rotor blade, and the sum of it is the total air force. Again, the direction of this force is not what we are interested in, and therefore we derive those vectors in a different way. First of all, we have the thrust again, that is in direction of the wind velocity, and perpendicular to that we have then this tangential force that is really what we are interested in, because that is turning our rotor.
Yeah, before carrying out an aerodynamic dimensioning, we have to explain some basics before. First, the aerofoil form ratio is defined, and this number is the ratio between the lift and the drag force. The maximum value, epsilon max, is a measure for the profile quality of the rotor blade. Good profiles reach values of approximately 120 and more, and for comparison, a normal shelf has a value of approximately 10. Epsilon max is usually reached when the lift force coefficient is in the range between 0.8 and 1.1. And in the design point, the profile shall work close to its best aerofoil form ratio, epsilon max. And this means that the drag force coefficient, Cw, is very small compared to the lift force coefficient, Ca. As a reminder, you can here see how the tangential force is calculated. The tangential force contains a term including the lift force coefficient and the drag force coefficient. And if the drag force coefficient is negligible small, it disappears here in the equation. And thus the tangential force reduces to the contribution of the lift force and is calculated according to this formula here. And this formula only contains the lift force coefficient. Thus, the following equation applies for the mechanical power. It is calculated by the number of the rotor blades Z, the circumferential velocity U, and the tangential force Ft. The maximum power that can be extracted from the circular ring area is calculated by the following equation. It is 16/27 times the air density divided by 2 times the wind velocity to the power of 3 times the circular ring area. And you can see the circular ring area here in the picture. Equating the mechanical and the bed's power leads to the optimal blade depth that you can see here.
And with the relationships that can be read from the wind triangle, that the Vw is equal to 3/2 VR sine of delta, and U is equal to omega r, that is equal VR cosine of delta, and after a few transformations we get then the optimum rotor blade depth Tb of r is 16p times the complete diameter of the or radius of the rotor blade divided by 9 Ca lambda and z, the number of rotor blades, times 1 divided the square root of lambda divided by the complete radius big R times the radius of the blade element to the square plus 4 divided by 9. And as a conclusion, due to this optimum blade depth design per blade element, the maximum power according to beds can be transmitted at its design point. And in the next video, as we have had here now so many formulas, Hanna will present an example in order to get more convenient with all those formulas. Thank you very much.